In the autumn of 79 Anno Domini, a wealthy banker named Lucius Caecilius Jucundus sat in his villa in Pompeii, carefully recording the day's transactions on wax tablets, utterly unaware that the mountain looming over his city had been preparing its response to human prosperity for more than 1700 years. The volcano that Romans called Vesuvius had last erupted in the Bronze Age, so long ago that no living memory, no written record, no oral tradition preserved any warning of what the mountain could do, and the fertile soil on its slopes had drawn farmers and vintners who praised the gods for such abundance, while building their lives on a sleeping apocalypse. That morning, as Caecilius tallied his considerable wealth, small tremors shook the inkwells on his desk, but earthquakes had rattled the region for 17 years, ever since the devastating quake of 62 had toppled temples and cracked the aqueducts, and the trembling earth had become as ordinary as the changing seasons. What neither Caecilius nor any philosopher in the empire understood was that, beneath his feet, at a depth of nearly 4 miles, a massive chamber of molten rock had been accumulating pressure for millennia, and the tremors he dismissed were the sound of the Earth's crust fracturing under unbearable strain, hairline cracks propagating through solid stone like lightning frozen in geological time. The magma chamber beneath Vesuvius contained approximately 3 cubic miles of molten material, heated to temperatures exceeding 2000 degrees Fahrenheit, a reservoir of liquid stone mixed with dissolved gases that existed under pressures capable of crushing steel into the density of lead, though steel as Caecilius knew it would not be invented for another 1,000 years. Within this subterranean prison, water vapour, carbon dioxide and sulphur compounds remained trapped in the melt, held in solution by the crushing weight of 4 vertical miles of rock. But as the magma slowly rose through fractures in the overlying strata, the decreasing pressure would allow these gases to exsolve, to come out of solution like bubbles forming in a bottle of wine when the cork is removed, except that the bottle was the size of a city and the cork was the entire mountain. The citizens of Pompeii had no concept of pressure, no understanding of gases, no scientific framework to comprehend that they lived atop a geological pressure cooker that had been building toward catastrophe since before Rome was founded, and the natural philosophers who might have observed and theorized were too busy debating the nature of the 4 elements to consider that earth and fire might combine in ways that could obliterate civilization. On the morning of August 24th, the mountain announced its intentions with a detonation that could be heard in Misenum, 20 miles across the bay, where the 17-year-old Pliny the Younger was studying while his uncle, Pliny the Elder, commander of the Roman fleet, was finishing his breakfast. The explosion that created this thunderous report released energy equivalent to 100,000 times the atomic bomb dropped on Hiroshima, though such comparisons would have meant nothing to the people experiencing the event who had no reference point for devastation on this scale, and whose cosmology explained such phenomena as the anger of Vulcan, the god of fire, working at his forge beneath the mountain. The eruption column that burst from Vesuvius rose at a velocity of 100 meters per second, a vertical jet of pulverized rock, glass fragments, and superheated gases that punched through the atmosphere like a battering ram, carrying ash and pumice into the stratosphere at an altitude of 21 miles, higher than any commercial aircraft would fly 2,000 years later. The column took on the appearance of an immense stone pine tree, its trunk rising straight and true before spreading into a canopy that would ultimately extend for hundreds of miles, and Pliny the Younger would describe this shape in his letters to the historian Tacitus, creating the term Plinian eruption that volcanologists would still use in the 21st century. What made this eruption column rise to such extraordinary heights was the phenomenon that modern scientists would call thermal buoyancy, the same principle that makes hot air balloons ascend, but on a scale that defied human comprehension even after the principles were understood. The fragmentary material ejected from the volcano, reduced to particles ranging from microscopic ash to fist-sized pumice stones, remained so hot that the mixture of rock and gas was actually less dense than the surrounding atmosphere, and this density contrast drove the column upward with self-sustaining force, each cubic meter of erupting material carrying enough heat energy to power a small city for a day. The violence of the fragmentation process occurred because of those dissolved gases that had been trapped in the magma, and as the molten rock ascended through the volcanic conduit, The decreasing pressure caused the gases to expand with such explosive force that they ripped the surrounding magma apart into billions of tiny shards, transforming solid stone into a foam of glass particles small enough to remain suspended in the atmosphere. The pumice that began to rain down on Pompeii was actually frozen foam, volcanic rock so filled with gas bubbles that it could float on water, and as the day progressed, these stones accumulated on roofs and in streets at a rate of 6 inches per hour. A silent, relentless burial that would eventually collapse buildings and trap those who had sought shelter indoors. Meanwhile, in the town of Herculaneum, situated on the western flank of Vesuvius, and slightly closer to the mountain than Pompeii, the inhabitants watched the towering eruption column with terror, but initially found themselves spared the pumice fall that devastated their neighbour city, because the prevailing winds carried the ejected material southeastward, away from their streets and homes. This accident of meteorology gave the citizens of Herculaneum false confidence, and many delayed their evacuation, gathering their valuables and debating whether to flee by land or wait for rescue by sea, unaware that the greatest danger was not the falling stones, but a phenomenon that would not be scientifically understood until French volcanologists studied Mount Pelée in the Caribbean nearly 2,000 years later. Inside the eruption column, the mixture of rock particles and gas was cooling, and as it cooled it became denser, and when portions of the column could no longer sustain their own weight against gravity, they collapsed, sending avalanches of superheated material racing down the mountainside at speeds exceeding 100 miles per hour, flows of rock and gas so hot that they could instantly carbonize wood and boil seawater, and so dense that they moved like fluid, wrapping around obstacles and filling every depression in the landscape. These pyroclastic surges, as they would be termed by scientists who studied their deposits, were perhaps the most lethal phenomenon that volcanoes could produce, combining temperatures of 400 degrees Celsius with hurricane-force winds and the abrasive power of billions of rock particles moving in unison. The first surge reached Herculaneum in the early hours of August 25th, after midnight, when many residents had taken shelter in boathouses along the beach, praying for dawn and rescue that would never arrive. The surge moved across the town in seconds, a glowing avalanche that entered every building, filled every room, and instantly killed every living thing through a combination of thermal shock and asphyxiation, heating the air in human lungs to temperatures that coagulated blood and seared tissue beyond any possibility of survival. The victims had no time to scream, no time to move, no time even to register what was happening, and their bodies were buried under 20 meters of volcanic material that would preserve them with such fidelity that 2 millennia later, scientists could study their bone structure, reconstruct their last meals, and determine their ages at death with precision that would have astounded the people themselves. The material that buried Herculaneum was not loose ash like the pumice that covered Pompeii, but a dense hot mixture that flowed like wet concrete and hardened into tuff, a rock-like substance that would protect the city's wooden structures, organic materials, and even papyrus scrolls in a way that dry ash never could, creating an archaeological time capsule of such extraordinary preservation that it would reshape understanding of Roman daily life when excavation finally began in 1738. Back in Pompeii, as the pumice continued to accumulate through the afternoon and into the night, reaching depths of 9 feet in some areas, the structural failure of buildings killed many who had chosen to shelter in place, but others fled into the darkness, wrapped in pillows tied to their heads, with cloth as improvised helmets against the falling stones, carrying what wealth they could manage while stumbling through streets illuminated only by the eerie orange glow of the eruption column overhead. Caecilius the banker, if he survived this long, would have faced an agonizing choice that thousands of his neighbors also confronted: abandon everything and flee immediately, or delay departure to gather more valuables, to search for separated family members, to make one more trip back into a collapsing house for items too precious to leave behind. The archaeological record suggests that many chose to go back, and that this decision killed them, because the pyroclastic surges that had destroyed Herculaneum eventually reached Pompeii as well, and those who had delayed their escape by even an hour found themselves trapped in a city filled with waist-deep pumice, unable to run, unable to climb over the debris, unable to do anything but die when the searing cloud enveloped them in the early morning hours. The casts made by Giuseppe Fiorelli in the 19th century, created by pouring plaster into the voids left by decomposed bodies in the hardened ash, captured the final moments of these victims with haunting intimacy, showing people who died while trying to protect children, while clutching bags of coins, while covering their faces against the heat and toxic gases, their postures frozen in time as permanent testimony to the last seconds of consciousness before the pyroclastic surge claimed them. What Caecilius and his contemporaries could never have known was that Vesuvius was merely one expression of a geological process that girdles the planet, a consequence of the Earth's internal heat and the slow, inexorable movement of the crustal plates that float on the semi-molten mantle below. The Italian peninsula exists because the African tectonic plate has been colliding with the Eurasian plate for millions of years, a collision that continues at a rate of approximately 1 inch per year, imperceptible to human observation but catastrophically powerful over geological time. And this collision creates a subduction zone where the denser oceanic portion of the African plate descends beneath Europe, plunging into the mantle where increasing temperature and pressure cause the rock to partially melt, and this melt, being less dense than the surrounding material, rises through the overlying crust to create the volcanoes that dot the Mediterranean region. This process, which would not be understood until the plate tectonics revolution of the 1960s, operates on every continent and beneath every ocean, creating the ring of fire that encircles the Pacific Ocean and the volcanic chains that mark every plate boundary where oceanic crust descends into the Earth's interior. And it means that volcanic eruptions are not aberrations or punishments from angry gods, but inevitable consequences of the Earth's thermal engine, as predictable in the long term as the rising of the sun, though maddeningly unpredictable in their precise timing. The amount of energy released by the Vesuvius eruption in 79 exceeded the total energy consumption of the entire Roman Empire for a year, concentrated into less than 24 hours, a staggering discharge of thermal and kinetic energy that originated from the radioactive decay of elements in the Earth's mantle and the residual heat from the planet's formation 4.5 billion years earlier. Every second during the height of the eruption, the volcano ejected approximately 1.5 million tons of material, a rate of mass discharge that would empty a modern supertanker in less than a minute, and this material reached the stratosphere where it spread across the northern hemisphere, creating spectacular sunsets as far away as China and causing measurable cooling of global temperatures for the following year. Though no one in the ancient world could connect their unusually cold summer to an eruption on the other side of their known world, the volcanic material itself represented a sampling of the Earth's interior, rock that had never seen sunlight until the eruption brought it to the surface, carrying within its crystal structure a record of the pressures and temperatures deep underground, and these rocks contain minerals like lucite and nepheline that could only form under specific conditions, making them valuable to volcanologists who would study them nearly 2,000 years later, searching for clues about the chemical composition and thermal state of the mantle beneath the Mediterranean. In the immediate aftermath of the eruption, as the column collapsed and the explosive phase ended, Vesuvius continued to smoulder and emit gases for weeks, and the region remained poisoned by toxic fumes and covered in a blanket of ash so thick that it transformed the landscape into an alien environment where nothing looked familiar and nothing grew. The Emperor Titus appointed a commission to oversee relief efforts and the redistribution of property from those who had died without heirs, but Pompeii and Herculaneum were never rebuilt, their locations eventually forgotten as new towns grew elsewhere, and the ash deposits were covered by vegetation and soil. And for more than 1,600 years, the cities existed only as footnotes in historical texts, their physical remains hidden beneath farmland and vineyards, waiting for an accidental discovery that would come in the late 16th century, when an architect digging a canal struck ancient walls and decided not to investigate further because the project was behind schedule. It would take another 150 years before systematic excavation began, and by then, the science of archaeology did not yet exist. So the early excavators treated the buried cities as treasure troves to be plundered, rather than crime scenes to be carefully documented, and countless artifacts were removed without recording their context, destroying information that could never be recovered. The study of Vesuvius and other volcanoes would gradually evolve from mythology to natural philosophy to experimental science, a transformation that took centuries and required the development of numerous supporting disciplines, including chemistry, physics, and geology, fields that did not exist as formal sciences until the Enlightenment and later. In 1631, Vesuvius erupted again after more than 500 years of dormancy, killing approximately 4,000 people and demonstrating that the mountain remained active, and this eruption prompted some of the first attempts at scientific observation of volcanic phenomena, though the observers lacked the theoretical framework to interpret what they were seeing. Natural philosophers noted that the eruption was preceded by earthquakes and the drying up of springs, and they observed that different types of material were ejected at different stages of the eruption, but without understanding pressure, gas solubility, or magma chemistry. They could only catalogue observations without explaining the underlying mechanisms. The prevailing theory held that volcanoes were caused by the combustion of sulfur and bitumen in underground caverns, an explanation that seemed reasonable given the smell of sulfur compounds in volcanic gases and the obvious presence of fire. But this theory could not explain where the enormous volumes of ejected rock came from, nor could it account for the specific sequence of events that characterized major eruptions. The recognition that volcanic rocks were not transformed sediments, but solidified magma that had originated deep within the Earth, represented a crucial conceptual breakthrough. But it required observers to accept that rocks could melt, a proposition that seemed absurd to many scholars who argued that the temperatures required to melt stone exceeded anything that could exist in nature. The debate between the Neptunists, who believed that all rocks formed from precipitation in a global ocean, and the Plutonists, who argued that many rocks originated from subterranean heat, dominated geology in the late 18th and early 19th centuries, and volcanoes provided the most dramatic evidence for the Plutonist position, since even the most determined Neptunist could not explain how the red-hot lava visibly flowing from Mount Etna had somehow precipitated from seawater. The chemist Sir Humphrey Davy conducted experiments in the early 1800s, demonstrating that basalt rock would melt when heated to approximately 1200 degrees Celsius, temperatures that seemed impossibly high, but were actually conservative estimates of the true temperature inside active lava flows, which can exceed 1300 degrees Celsius, and these experiments helped establish that the Earth's interior was indeed hot enough to maintain reservoirs of molten rock. The realization that the Earth's interior was molten or partially molten raised profound questions about the planet's age and thermal history, questions that would not be satisfactorily answered until the discovery of radioactive decay in the early 20th century provided a heat source that could maintain high temperatures over billions of years. Before this discovery, physicists like Lord Kelvin calculated that if the Earth was simply cooling from an initially molten state, as many theories proposed, it could not be more than a few tens of millions of years old, a conclusion that conflicted catastrophically with the geological evidence for gradual processes operating over vastly longer timescales, and with the biological evidence for evolution, which also required immense spans of time. The discovery that radioactive elements like uranium and thorium, present in trace amounts throughout the Earth's mantle and crust, continuously generate heat as they decay, solved this thermal crisis, and explained why the Earth remains geologically active after more than 4 billion years, why volcanoes still erupt and continents still drift and earthquakes still shake the ground, phenomena that would have ceased long ago if the planet were merely cooling without an internal heat source. The distribution of volcanoes across the Earth's surface is not random, but follows patterns that became increasingly obvious as global exploration and mapping improved during the 19th and 20th centuries. With the vast majority of active volcanoes located either along the boundaries between tectonic plates or above hotspots, relatively stationary plumes of hot mantle material that rise from deep within the Earth's interior. The ring of fire encircling the Pacific Ocean and including volcanoes in Japan, the Philippines, Indonesia, New Zealand, the west coast of South America, Central America, Mexico, and the Pacific Northwest of North America, represents the world's most active volcanic region, containing approximately 75% of the planet's active volcanoes and experiencing 90% of all earthquakes, a concentration of geological violence that results from the systematic subduction of oceanic plates beneath the surrounding continental margins. The Indonesian archipelago alone contains more than 120 active volcanoes, more than any other nation, a consequence of its location, where the Indo-Australian plate subducts beneath the Eurasian plate, and the people of Indonesia have learned to live with volcanic hazards through generations of experience, though this accumulated wisdom has not prevented catastrophic death tolls when the largest eruptions occur. In 1815, Mount Tambora on the Indonesian island of Sumbawa erupted in what remains the most powerful volcanic event in recorded human history, ejecting approximately 40 cubic miles of material into the atmosphere, more than 10 times the volume released by Vesuvius in 79, and the explosion was heard on Sumatra 1,200 miles away, a distance equivalent to hearing a sound in New York City from Atlanta. The eruption column reached an altitude of 28 miles, penetrating well into the stratosphere where the ejected sulfur dioxide would be converted into sulfuric acid aerosols that would remain suspended for years, spreading across the globe and reflecting incoming solar radiation back into space with such efficiency that global temperatures dropped by as much as 3 degrees Celsius the following year. The year 1816 became known as the year without a summer in Europe and North America, where snow fell in June, crops failed across the northern hemisphere, and famine killed tens of thousands in what would be the worst climate disaster caused by a volcanic eruption in historical times. Though the people experiencing the crop failures had no idea that a volcano on an island they had never heard of was responsible for their suffering. In Indonesia, the immediate death toll exceeded 70,000, most dying not from the eruption itself but from the subsequent famine as ash smothered cropland across the region. And the Tambora eruption effectively destroyed the civilization that had existed on Sumbawa, eliminating languages and cultural traditions that were never recorded and can never be recovered. The Tambora eruption demonstrated that large volcanic events could have global climatic consequences, a realization that would gain increasing significance as scientists began to understand that Earth's climate system could be perturbed by relatively small changes in the energy balance between incoming solar radiation and outgoing thermal radiation. The sulfuric acid aerosols created when volcanic sulfur dioxide reaches the stratosphere remain suspended for years because the stratosphere lacks the weather systems that cleanse the lower atmosphere, and these aerosols, consisting of tiny droplets, only micrometers in diameter, scatter and reflect sunlight with remarkable efficiency, reducing the amount of solar energy reaching the Earth's surface and causing measurable cooling that can persist for several years after a major eruption. The eruption of Mount Pinatubo in the Philippines in 1991 provided modern science with the opportunity to observe this process with sophisticated instruments, and satellites measured a global temperature decrease of approximately 0.5 degrees Celsius in the year following the eruption, confirming theoretical predictions and providing valuable data for climate models that attempt to quantify the various factors influencing Earth's temperature. The Pinatubo data also helped scientists understand that while volcanic eruptions can cause significant short-term cooling, the effect is temporary because the aerosols eventually settle out of the atmosphere, whereas carbon dioxide from human activities accumulates and persists, creating a long-term warming trend that overwhelms the temporary volcanic cooling. The mechanisms by which magma forms beneath the Earth's surface vary depending on the tectonic setting, but all involve the partial melting of mantle rock under conditions where either the temperature increases, the pressure decreases, or water and other volatiles lower the melting point of the minerals involved. In subduction zones where oceanic crust descends into the mantle, the subducting slab carries water bound in minerals that formed when seawater circulated through cracks in the oceanic crust, and as the slab descends and heats up, this water is released and rises into the overlying mantle wedge, where it dramatically lowers the melting point of the peridotite rock that constitutes the mantle, causing partial melting, even though the temperature is not significantly higher than in adjacent areas where no melting occurs. This water-induced melting produces magmas that are relatively rich in silica and dissolved volatiles, making them viscous and prone to explosive eruptions when they reach the surface, and this explains why subduction zone volcanoes like Vesuvius, Krakatoa, and Mount St. Helens tend to produce the most violent and dangerous eruptions, whereas volcanoes at divergent plate boundaries or above hotspots, where water plays a lesser role and the magma is less silica-rich, tend to erupt more gently with fluid lava flows rather than explosive ash columns. The island of Iceland provides a natural laboratory for studying volcanic processes because it sits astride the mid-Atlantic ridge, a divergent plate boundary where the North American and Eurasian plates are pulling apart at a rate of approximately 1 inch per year, and it also sits above a mantle hotspot, creating an unusual combination of tectonic settings that generates prodigious amounts of magma and makes Iceland one of the most volcanically active regions on Earth, despite its location far from any subduction zone. The Laki Fissure eruption of 1783, One of Iceland's most significant historical eruptions released approximately 3.5 cubic miles of lava over the course of 8 months, covering an area of more than 200 square miles with basalt flows, and releasing enormous quantities of sulfur dioxide that created a persistent haze across Europe and contributed to crop failures and famine. The Laki eruption killed approximately 1/4 of Iceland's population, most dying from famine after the volcanic gases and ash destroyed pastures and poisoned livestock, and the eruption may have contributed to social unrest in France that would culminate in the Revolution of 1789, since the crop failures and harsh winters that followed the eruption exacerbated existing economic problems and increased food prices at a time when the French monarchy was already facing fiscal crisis. This connection between volcanic eruptions and political upheaval illustrates how natural disasters can have cascading consequences that extend far beyond the immediate physical damage, influencing human history in ways that the participants in those events could not recognize, because they lacked the global perspective and scientific knowledge to connect distant phenomena. The explosive power of volcanic eruptions depends critically on the gas content of the magma and the ability of those gases to escape, a relationship that creates a fundamental distinction between effusive eruptions that produce lava flows and explosive eruptions that produce ash and pumice. Magma ascending from depth contains dissolved gases, primarily water vapor, carbon dioxide, and sulfur dioxide, held in solution by the enormous pressure of the overlying rock. But as the magma rises and pressure decreases, these gases exsolve and form bubbles, and if the magma is fluid enough, the bubbles can rise through the liquid and escape relatively peacefully at the surface, producing the lava fountains and flows characteristic of Hawaiian and Icelandic eruptions. However, if the magma is viscous, with a high silica content that creates strong molecular bonds between silicon and oxygen atoms, the gas bubbles cannot escape easily, and pressure builds within the ascending magma until it exceeds the strength of the surrounding rock, at which point the magma explodes, fragmenting into billions of tiny particles that are ejected at velocities that can exceed the speed of sound. This fragmentation process converts thermal and chemical energy into kinetic energy with terrifying efficiency, accelerating volcanic material from rest to hundreds of meters per second in fractions of a second, and the resulting eruption column carries this material to altitudes determined by the balance between the upward momentum and thermal buoyancy of the erupting mixture and the downward pull of gravity. The largest explosive eruptions, termed supereruptions by volcanologists, eject more than 240 cubic miles of material and represent the most catastrophic natural disasters the planet can produce, capable of devastating continental-scale areas and causing global climate disruption that persists for years or even decades. The Toba supereruption, which occurred in Sumatra approximately 74,000 years ago, ejected an estimated 670 cubic miles of material and left behind a caldera that now contains Indonesia's largest lake, and genetic evidence suggests that this eruption may have reduced the global human population to perhaps 10,000 individuals, creating a genetic bottleneck whose effects can still be detected in the DNA of modern humans. The volcanic winter following the Toba eruption may have lasted for years, with temperatures dropping by as much as 15 degrees Celsius in some regions, and the combination of cold temperatures, reduced sunlight, and acid rain falling from a stratosphere loaded with volcanic aerosols would have created environmental conditions that pushed human populations to the brink of extinction, though the precise magnitude and duration of the climate effects remain subjects of active scientific debate, because the evidence is fragmentary and open to multiple interpretations. The recognition that supereruptions have occurred repeatedly throughout Earth's history, and that several volcanic systems currently capable of producing such events remain active, creates obvious concerns about the potential for future catastrophes, though the probability of a supereruption occurring in any given year is extremely low, on the order of 1 in 100,000. The Yellowstone volcanic system in Wyoming sits above a hotspot that has produced 3 supereruptions in the past 2 million years, the most recent occurring approximately 640,000 years ago, and the presence of an active magma chamber beneath Yellowstone, detected by seismic imaging and confirmed by the thermal features like geysers and hot springs that make the region famous, indicates that the system remains capable of producing future eruptions. However, the monitoring data collected over decades shows no evidence that an eruption is imminent or even likely in the foreseeable human future, and the most probable volcanic events at Yellowstone in the coming centuries would be relatively small lava flows rather than catastrophic explosive eruptions, though the persistence of popular anxiety about Yellowstone illustrates how difficult it is to communicate probabilistic risk to the general public, who tend to focus on worst-case scenarios while discounting their actual likelihood. The problem of forecasting volcanic eruptions, predicting not just that a volcano will eventually erupt, but when it will erupt and how large the eruption will be, has occupied scientists since volcanology emerged as a distinct discipline in the early 20th century, and despite significant advances in monitoring techniques and theoretical understanding, eruption forecasting remains as much an art as a science, requiring experienced judgment to interpret ambiguous signals that could indicate either an impending eruption or merely normal background activity. Volcanoes typically provide warning signs before major eruptions, including increased seismicity as magma fractures rock on its way to the surface, ground deformation as the accumulating magma inflates the volcanic edifice, changes in gas emissions as the magma degasses, and increased thermal activity as hot material approaches the surface. But these signals can be subtle, ambiguous, or contradictory, and volcanoes sometimes show all the signs of an imminent eruption only to return to quiescence without erupting, while other volcanoes erupt with minimal advance warning. The 1985 eruption of Nevado del Ruiz in Colombia killed more than 23,000 people, despite the presence of monitoring equipment and scientists who had warned of the danger. Because the warnings were not effectively communicated to civil authorities, the recommended evacuations were not ordered in time, and the deadly lahars, volcanic mud flows, generated when the eruption melted the mountain's glacial ice cap reached the town of Armero faster than anyone anticipated, arriving in the middle of the night and burying most of the population before they could escape. Lahars represent one of the most insidious volcanic hazards because they can travel many miles from the volcano, following river valleys and inundating areas that seem safely distant from the erupting vent, and their fluid behavior allows them to flow around obstacles and fill depressions with a mixture of water, volcanic ash, and rock debris that has the consistency of wet concrete and can bury buildings to their roofs. The lahars that swept down Mount Rainier in Washington approximately 500 years ago, before European contact with the region, travelled more than 60 miles from the volcano and covered areas that are now occupied by suburbs of Seattle and Tacoma, creating deposits tens of feet thick that remain visible in road cuts and stream banks, and the geological evidence indicates that Mount Rainier has produced such lahars repeatedly throughout its history. With recurrence intervals of hundreds to thousands of years, the presence of more than 3 million people now living in areas that have been inundated by lahars in the geologically recent past creates a risk scenario that emergency planners find deeply troubling, because a large lahar could travel from the mountain to populated areas in less than 2 hours, leaving minimal time for evacuation, and the warning systems designed to detect such events have never been tested under actual emergency conditions and might fail in unpredictable ways when confronted with the chaos of a real disaster. The volcanic hazards that threaten modern cities are not fundamentally different from those that destroyed Pompeii and Herculaneum nearly 2,000 years ago, but the scale of potential casualties has increased enormously because of population growth and urbanization, and many of the world's most dangerous volcanoes now have major cities built on or near them, creating exposure to risk that would have been unimaginable in the ancient world. The Tokyo-Yokohama metropolitan area, home to more than 38 million people, sits within range of several active volcanoes including Mount Fuji, which last erupted in 1707 and ejected enough ash to cover Edo, the predecessor of modern Tokyo, with several inches of volcanic debris. And while a repeat of the 1707 eruption would not directly threaten most of the metropolitan area with lava flows or pyroclastic surges, the ashfall could shut down transportation systems, collapse roofs, contaminate water supplies, and disrupt electrical grids, creating cascading failures that would affect millions of people and potentially cause economic losses exceeding $1 trillion. The eruption of Mount Pinatubo in 1991, despite killing fewer than 1,000 people directly, caused approximately $10 billion in economic damage and forced the permanent evacuation of more than 200,000 people, demonstrating that modern societies remain vulnerable to volcanic disasters despite technological advances, and in some ways are more vulnerable because of their dependence on infrastructure systems that can be disrupted by even moderate ashfall. The increasing sophistication of volcanic monitoring has not translated into foolproof eruption prediction, because the processes occurring beneath volcanoes are extraordinarily complex, involving the behavior of multi-phase fluids at extreme temperatures and pressures in geological structures that cannot be directly observed and must be inferred from surface measurements that provide only indirect and incomplete information about conditions at depth. A typical volcano monitoring program might include seismometers to detect earthquakes caused by magma movement, GPS stations to measure ground deformation, gas sensors to monitor changes in emissions, thermal cameras to detect heat anomalies, and satellite radar to measure changes in ground elevation with millimeter precision. But integrating these diverse data streams into a coherent picture of what the volcano is doing requires sophisticated analysis and often yields ambiguous results. The seismic signals generated by fluid movement in volcanic systems differ from those produced by brittle fracture of rock, creating distinctive earthquake types that include long-period events with gradually decaying oscillations and volcanic tremor consisting of continuous ground shaking that can persist for hours or days. An experienced seismologist can often infer from the character of these signals whether magma is moving and how quickly. But the relationship between seismicity and eruption timing is not deterministic. An increased earthquake activity might indicate that an eruption will occur within hours or weeks, or not at all if the magma stalls at depth without reaching the surface. The economic and political pressures surrounding eruption warnings create situations where scientists must make recommendations based on incomplete information, while knowing that a false alarm can cause enormous economic disruption and undermine credibility for future warnings. But a failure to warn can result in catastrophic loss of life, and this asymmetric risk calculation has led to both overcautious approaches where warnings are issued for eruptions that never materialize, and overly optimistic assessments where the danger is downplayed until it is too late to evacuate effectively. The evacuation of approximately 60,000 people from the area around Mount Pinatubo in June 1991, based on monitoring data that indicated an eruption was imminent but could not predict its exact timing or magnitude, represents one of the great success stories in volcanology, where scientists and civil authorities worked together effectively to move people out of harm's way days before the climactic eruption. But this success required a convergence of favourable circumstances, including cooperative government officials, available transportation, places to evacuate people to, and a population willing to leave their homes based on warnings about an invisible threat. Conditions that do not always exist in volcanic crises. The study of past eruptions through the geological record provides essential context for assessing volcanic hazards, because written historical records extend back only a few thousand years at most, and for many volcanoes much less than that, while the geological record preserves evidence of eruptions extending back millions of years, allowing scientists to establish the long-term behavior patterns of volcanic systems and to identify prehistoric eruptions far larger than anything witnessed in historical times. The techniques of tephrochronology, dating and correlating volcanic ash layers found in soil profiles, lake sediments, and ice cores have revealed that explosive eruptions inject chemically distinctive ash into the atmosphere that can be deposited hundreds or even thousands of miles from the source, creating marker horizons that can be used to establish precise chronologies for past environmental changes in human prehistory, and some key ash layers, like the Campanian ignimbrite deposited by a super eruption near Naples approximately 40,000 years ago, can be identified across the Mediterranean region and into Eastern Europe, providing a synchronous time marker that archaeologists use to correlate sites and to test hypotheses about human population movements and cultural transitions. The realization that volcanic eruptions have influenced human evolution and migration represents a relatively recent development in both volcanology and paleoanthropology, fields that historically operated independently, but have increasingly recognized that major volcanic events occurred at critical junctures in human prehistory, and may have shaped the course of evolution by creating environmental pressures that favored certain adaptations, or by fragmenting populations and creating the geographical isolation necessary for speciation. The discovery of Australopithecus fossils preserved in volcanic ash deposits in the East African Rift Valley, an actively spreading tectonic zone characterized by extensive volcanism, demonstrates that our early ancestors lived in volcanically active landscapes and witnessed eruptions, and the ash layers interbedded with fossil-bearing sediments provide precise dates for the fossils, and preserve information about the ancient environment, including pollen, plant fossils, and chemical signatures that reveal what the climate was like when our ancestors lived there. The East African Rift, created by tectonic forces pulling the continent apart at a rate of a few millimeters per year, contains a chain of volcanoes including Oldoinyo Lengai, the only volcano on Earth currently erupting carbonatite lava, a bizarre type of magma with such low silica content and low viscosity that it flows like water and is so rich in sodium and potassium carbonates that it resembles molten washing soda and creates black lava flows that turn white when the carbonates react with moisture in the air. The chemical diversity of volcanic rocks reflects the diversity of processes that create magmas and modify them as they ascend toward the surface, and the detailed study of volcanic rock chemistry has revealed that most magmas do not erupt immediately after forming, but spend extended periods, sometimes thousands of years, stored in crustal magma chambers where they cool, crystallize, mix with other magmas, assimilate surrounding rock, and separate into layers of different composition through processes collectively termed magmatic differentiation. The crystals that form as magma cools have different densities than the surrounding liquid, and dense crystals like olivine and pyroxene tend to sink, while light crystals like plagioclase tend to float. And this gravitational separation, combined with the tendency of crystals to have different compositions than the liquid they crystallize from, can transform a magma chamber over time from a relatively homogeneous reservoir of basaltic magma into a stratified system with dense, iron-rich magma at the bottom and light, silica-rich magma at the top. And when such a stratified chamber erupts, the silica-rich magma emerges first, producing light-coloured pumice and ash, followed by progressively darker material as the eruption taps deeper levels of the chamber, creating deposits with systematic compositional variations that record the pre-eruption structure of the magma reservoir. The discovery of zoned crystals in volcanic rocks, individual mineral grains showing complex internal structures with cores of one composition surrounded by rims of different composition, has revolutionized understanding of magma chamber processes by revealing that crystals experience changing conditions during their residence in the chamber, perhaps starting to grow in one part of the system before being transported to another part where they continue growing under different conditions. And the detailed analysis of these growth zones, using techniques like electron microprobe analysis that can measure chemical composition at the micron scale, allows scientists to reconstruct the thermal and chemical history of individual crystals and to determine how long they spent in the magma chamber before being erupted. Some crystals contain radioactive elements, whose decay products accumulate at predictable rates, allowing the calculation of how long ago the crystal formed, and these crystal ages sometimes exceed the age of the eruption by hundreds of thousands of years, indicating that crystals can be recycled through magma systems repeatedly, being incorporated into new magma batches and surviving multiple cycles of partial melting and crystallization. And these ancient crystals serve as archives of long-term magmatic processes and provide glimpses into the deep crustal environment where magmas originate and evolve. The relationship between volcanism and the formation of ore deposits has made certain volcanic regions enormously valuable from a resource perspective, because the hydrothermal systems driven by volcanic heat can concentrate metals like copper, gold, silver, lead, and zinc from large volumes of rock into small, intensely mineralized zones that can be economically mined. The circulation of heated groundwater through fractured volcanic rock, driven by the temperature gradient created by underlying magma, leaches metals from the rock through which it passes, and when this metal-bearing fluid encounters changing temperature, pressure, or chemical conditions, the dissolved metals precipitate, forming ore minerals that accumulate in fractures, creating vein deposits, or replacing existing rock, creating massive sulfide deposits that can be extraordinarily rich in valuable metals. The silver deposits at Potosí in Bolivia, discovered by Spanish colonizers in 1545 and worked continuously for centuries, formed in association with volcanic activity approximately 13 million years ago, and the mountain at Potosí produced so much silver that it funded the Spanish Empire for generations and became a byword for extraordinary wealth, though the mining conditions killed countless indigenous workers forced to labor in the mines under conditions that amounted to a death sentence, and the wealth extracted from Potosí never benefited the local population, but flowed to Spain where it funded wars and courtly extravagance, before dissipating in inflation as the flood of precious metals destabilized European economies The recognition that volcanic eruptions can create valuable mineral deposits as well as destroy lives and property adds a layer of complexity to human relationships with volcanoes, because volcanic soils are often extraordinarily fertile due to their content of minerals and nutrients. Volcanic landscapes can harbour valuable ore deposits. Volcanic heat can be harnessed for geothermal energy production, and volcanic rocks themselves can be valuable construction materials, creating powerful economic incentives for people to live near volcanoes despite the risks. And this risk-benefit calculation has been made by human communities for thousands of years. From the ancient Romans who built cities on the slopes of Vesuvius to modern Indonesians who farm the fertile volcanic soils of Java despite living in one of the most volcanically active regions on Earth. The population density in volcanic regions of Indonesia exceeds 1,000 people per square kilometre in some areas, among the highest rural population densities on Earth, and this concentration of people on volcanic slopes reflects both the agricultural productivity made possible by volcanic soils and the lack of alternative land in a region where population growth has been rapid and arable land is limited, creating a situation where people knowingly accept volcanic risk because the alternatives are worse, and where volcanic eruptions that would depopulate equivalent areas in wealthier countries result in people returning to rebuild in the same dangerous locations because they have nowhere else to go. The concept of acceptable risk varies enormously across cultures and economic circumstances, and what seems like irrational behaviour to outside observers, building homes on the flanks of active volcanoes, farming land that has been devastated by eruptions within living memory, refusing to evacuate when warned of impending danger, often reflects rational calculations based on different priorities and constraints, where the certainty of poverty and landlessness if one leaves outweighs the uncertain possibility of death if one stays, and where cultural and emotional attachments to ancestral land create bonds that transcend rational risk assessment. The evacuation zones around some active volcanoes remain permanently populated despite official prohibitions, because the residents have decided, consciously or not, that they would rather live at risk in a familiar place than safely in exile, and forcing people to leave their homes based on statistical risk calculations that are meaningless at the individual level raises profound ethical questions about paternalism, autonomy, and the rights of people to make their own choices, even when those choices seem objectively foolish to experts, armed with scientific knowledge and probability theory. The volcanic features that pose the greatest danger to human populations, stratovolcanoes with steep slopes built of alternating layers of lava and ash, characterized by viscous magma and explosive eruptions, are the same features that create the most spectacular mountain scenery, and many of the world's most beautiful and iconic mountains are active or dormant volcanoes, including Fuji in Japan, Rainier in the United States, Cotopaxi in Ecuador, and Kilimanjaro in Tanzania. And this aesthetic appeal, combined with the recreational opportunities provided by volcanic mountains, has made many dangerous volcanoes into major tourist destinations, creating a situation where tens of thousands of people might be present on a volcano on any given day during the tourist season, most of them completely unaware that they are standing on an active volcanic system that has killed people in the past and will certainly kill people again in the future. Mount Ontek in Japan erupted without warning in September 2014, killing 63 hikers who were near the summit enjoying the autumn colours, and the eruption was a relatively small phreatic event, caused by steam explosions when groundwater flashed to vapour rather than by rising magma. But it demonstrated that even small eruptions can be deadly when they occur without warning in places where people are present, and that the monitoring systems designed to detect magmatic eruptions may not provide useful warning for steam-driven events that can occur rapidly without the extended precursory activity that typically precedes magmatic eruptions. The increasing precision of volcano monitoring technology has paradoxically made eruption prediction more difficult in some ways, because the high-quality data now available reveal just how complex volcanic systems are and how many different processes can produce similar observable signals, and the temptation to believe that more data will necessarily lead to better predictions has not been borne out by experience, which shows that understanding what data mean requires theoretical models of volcanic processes that remain incomplete and contested. The seismic signals detected before the Mount St. Helens eruption of 1980 showed clear evidence of magma movement and provided several weeks of warning that an eruption was likely, but they could not predict the magnitude of the eruption, or the fact that it would begin with a massive landslide that removed the entire north face of the mountain, creating a lateral blast that devastated an area of more than 200 square miles and killed 57 people, including David Johnston, a young USGS volcanologist who was stationed at an observation post that was considered to be at a safe distance from the volcano. Johnston's death, along with that of photographer Reed Blackburn and numerous others who thought they were safely outside the danger zone, demonstrated that volcanoes can produce hazards that extend far beyond the areas identified as high risk based on previous behaviour, and that the geological record, while useful, may not capture the full range of possible eruptive scenarios, especially for volcanoes that erupt infrequently and whose historical record covers only a small sample of their long-term behaviour. The Mount St. Helens eruption fundamentally changed volcanology as a discipline, providing the first opportunity to study a major explosive eruption with modern instruments and generating datasets that would be analysed for decades, revealing new phenomena and forcing revisions to theoretical models that had seemed well established. The discovery that the eruption was triggered by a landslide rather than being purely a magmatic phenomenon led to increased attention to volcano stability and to the recognition that volcanic edifices are inherently unstable structures, steep mountains built of weak materials including loose ash and lava flows that have been altered by circulating hydrothermal fluids into clay minerals that have little strength, and that sector collapses, where an entire flank of a volcano fails and slides away in a massive landslide, are relatively common events in the geological history of many volcanoes, even though they are rare on human timescales. The deposits of ancient sector collapses have been identified at volcanoes around the world, forming distinctive hummocky terrain that extends for tens of miles from the source volcano, and the recognition that such collapses can occur has led to reassessment of hazard zones around many volcanoes, and to uncomfortable realizations that areas previously considered safe might actually be vulnerable to hazards that occur too infrequently to be well represented in the historical record. The concept of recurrence intervals, the average time between events of a particular magnitude, provides a useful framework for thinking about volcanic hazards, but it can be misleading because it suggests a regularity that does not exist, and the fact that a volcano has not produced a major eruption in 500 years does not mean that an eruption is due, or that the next eruption is more likely now than it was 100 years ago, because volcanic processes are not cyclic in a predictable way, and the triggers for eruptions can be external factors like earthquakes that occur randomly, rather than on a schedule. The probabilistic volcanic hazard assessment, which attempts to quantify the likelihood of different eruptive scenarios based on the geological record and theoretical understanding of volcanic processes, represents the state-of-the-art in volcanic hazard evaluation. But these assessments are only as good as the data and models they are based on, and they typically carry large uncertainties that are sometimes glossed over when the results are communicated to decision-makers and the public, who tend to want definite answers to questions like when will this volcano erupt and how bad will it be, that scientists cannot provide with the precision that stakeholders desire.